course, I used to give superconductivity lectures 32 hours here in ISER, Pune, and elsewhere. So there will be a few equations and maths, but I would, you don't have to go through all of them. And the slides are with Dr. Manoj, and you can have a look at it later. So, want of time, I'm not going to derive many things. I'm going to write it up and then show you the results and explain the results rather than deriving many things. So, let me just start from the beginning. So, so there are few books which I'm going to give you. The first one is really a classic book on superconductivity by Michael Tingham. The second one is slightly at a BSc level, Rosinus and Rodrigues. It's a good book to understand basic concept of superconductivity. The next one is Superconductivity by edited by Benjamin and Ketterson. It has a lot of review articles from various people who worked on it. Fourth one is a classic. It is a Superconductive Metals and Alloys by Nobel laureate P.D. Guinness. Then you have superfluidity and superconductivity. Then you have a collection of volume of superconductivity by R.D. Parks. The last one is not a book. It's a very nice article by Ginsberg, which gives you a history of superconductivity, how it happened and how it was discovered and what were the things there. So it was 25 years ago, but it's a nice historical article. I would like you to read if you have time. So let me just go to the part there. So I think most of you know that Cameron owns liquefied helium at 1908. And soon after his discovery, he wanted to use this low temperature to study properties of materials at low temperature. So those days, mercury is the purest element which they can distill and get it to 59 or 69 pure, 99.999 pure. So he wanted to look at the resistivity of mercury at low temperature. So surprisingly, he could discover superconductivity. So everybody knows this figure. I think most of the superconductivity talk, you will see this. But what the many people don't tell you is that how difficult was this measurement? You know, we have to measure down to something like 10 microohms, and that is in nearly 100 years ago. Okay, so it was a very difficult experiment in many ways. Giles Hose was a student of Camerling owners. Somehow he didn't feature into the Nobel Prize list. The difficulty is that mercury is only 1 microohm centimeter at 300 K. And as you cool this mercury, it will go down in resistance. It will go by a factor of nearly 100 as you go towards 5 Kelvin or so. So we need to have sufficiently large resistance at room temperature of this mercury. How do you do that? You put it in narrow capillary, and it so happened that the capillary height is about 12.5 centimeters. And you want to perform resistivity measurements on this, and so that you can have a measurable resistance before it goes to a superconducting state. So it's a very tough experiment in 1911. Okay, so that Gulf's host, driven by Camerling owners, were able to measure. Then they show a sharp transition, which is at 4.2 K, which became the superconductivity of mercury. And there are some interesting accounts which I have given here, which is given in this article. Then soon afterwards, many people have seen superconductivity in various elements. And the superconductivity seems to be a ubiquitous phenomenon. It's there in nearly two-thirds of the periodic table is superconducting one way or the other. It could be at ambient pressure, which is that green shaded ones. It could be under pressure, which is yellow shaded, or it could be in thin film form. So you can see that nearly two-thirds of the periodic table, the superconducting state seems to be the ground state, except manganese, iron, cobalt. Incidentally, manganese, iron at 2.1 GPa, it shows superconductivity at 2 Kelvin. So you pressurize it, the magnetism gets lost, you get into a superconducting state. Of course, the only element which is very unusual is this bismuth. Bismuth under pressure is superconducting, as mentioned. So this was mentioned by Dr. Manoj Kumar. Why bismuth is strange in compared to other metals in the periodic table is because the carrier density is 5 orders of less than the carrier density of normal metals. 10 to the power of 22 electrons for the normal metals. Bismuth is 5 orders of magnitude smaller. So people thought that bismuth is not going to superconduct and so on. And certainly, if it superconducts, it's not going to be the BCS theory, which I am going to tell you in the next class. So, so people thought that it is not going to do that superconducting, and we showed that it is superconducting below 500 microkelvin, and the mechanism is different there. Okay, so let me just go to the current history of superconductivity. So this is before 1985. The superconductivity was largely confined to metals, transition metals and so on and so forth. And you can see that the year-wise, it is sort of a linear increase, right? And then the oxides came, superconductivity of YBCO, BISCO, lanthanum copper oxide, and so on. So the TC rapidly jumped up. Under pressure, the mercury was superconducting at 30 GPa. And then came very recently that high pressure at 250 gigapascal, the H3S is superconducting, and then slowly, right now the record is 267 GPa, which is lanthanum, sorry, 190 GPa, which is the lanthanum hydride. This is turned out to be not a superconductor. This is a false result, which was reported, but then it was not. Now it is taken back. So high pressure does show superconductivity close to room temperature. The holy grail of superconductivity is to find room temperature superconductor. But there are few. So he is the father of the low temperature superconductors. His name is Bernard Mathias. He is the one who discovered right from 1960s to nearly 80s many transition metal superconductors. And then Bednarz and Muller came and they showed the oxides, took over from there. It is not simply the TC which is important here. See, when you see the oxide materials which are showing superconductivity, it's entirely new mechanism of superconductivity. It brings us new physics ideas. It's just not simply you are increasing the TC, you are bringing new concepts in physics. That is what is very important here. The oxides really brought many new theoretical concepts and so on. So superconductivity is really an experimentally driven research. I mean, you find newer materials, then the theorists will jump in and show you that, okay, this can be understood by this mechanism and so on. The only exception is these hydrides. Hydrides were predicted. Actually, metallic hydrogen is under heavy pressure. It's supposed to show superconductivity close to room temperature. Nobody could get a metallic hydrogen, make it stable at such high pressures. So instead of looking at hydrogen, they look at hydrides and then found superconductivity at very high temperatures. 250 Kelvin, 260 Kelvin is the lanthanum hydride. That seems to be the record at high pressures. And so this research is going on, but at the same time, quietly, there are these quench contents carbon, boron addition. You can add maybe 30, 35% of boron to this amorphous carbon, then you can reach to 55 Kelvin at ambient pressure. So though it's not as high as the hydrides, but there is interesting physics, and it is good to look at it because it is at ambient pressure. So this is the history of superconductor. And of course, this is the discovery of bismuth, which I mentioned to you. So the room temperature is somewhere here. The race is on to squeeze hydrides to higher and higher pressures to reach room temperature superconductivity. So the latest is 1 week old. This is the new results from the Houston group, published in just a 1 week before in PNAS. So what they did was to take this mercury oxide superconductor. We call it HC1223. It's called HC12213. That initially at ambient pressure is supposed to show at 130 Kelvin or so. They apply a high pressure of 300,000 bar, and then the TC increases. And when they do a pressure quenching, that is suddenly release the pressure, it seems to still retain this metastable superconducting state. So what they have achieved is that from 133 Kelvin to 151 Kelvin, applying this 300,000 bar, and then quench this pressure so that it remains in a metastable state. So this seems to be an interesting way one can raise this superconducting TC. So as I said, superconductivity is more than 100 years old. It has developed into many things now. There are many kinds of superconductors. One is phononic. Phonon means lattice vibrations. So quantized lattice vibration. So the superconductivity comes because electrons are paired. So there is a binding energy of these electrons. There could be several glues for this. Phonons could be a glue to, because electrons cannot bind bound together unless it overcomes the Coulombic repulsion, no? Because they have the same charge. So the phonons act as a glue. There could be non-phononic glues as well. So if you look at the today's scenario, you have superconductors which explained by BCS theory, and there are some superconductors which cannot be explained by superconductors, which are doped semiconductors, ionic insulators, hydrides, high pressures. Then you have non-adiabatic system. We will come to the understanding what is non-adiabatic and adiabatic when we talk about BCS theory. So these are low carrier systems which are not expected to be a superconductor, and yet it is showing superconducting. Then you have non-phonon mechanism of superconductors like cuprates, nickelates. Then there are things known as heavy fermions, and sorry, and you have organic superconductors, iron-based chalcogenides, interface superconductivity. That is, you take lanthanum, lanthanum oxides, and then a strontium based oxide. You put a one over the top. The interface of this is superconducting, and so that's called interface superconductivity. Then you have twisted layer of graphene. You have one graphene layer, and then you put another angle, other layer in a magic angle. That shows superconductivity. Then you have topological superconductors. I guess somebody will talk about that in this faculty program. Then you have a celestial superconductivity. I call it celestial superconductivity because the superconductivity exists in neutron stars. Okay, so superconductivity today is a very vast subject, and it occurs in many ways. And to understand the superconductivity, let's look at the resistivity of materials. So, if you look at the resistivity of materials, the normal resistance, you see that it decreases as a function of temperature. Then, depending on you have alkali or transition metals, the low temperature goes as T to the power of 5 or T to the power of cube. Whereas in superconductor, It follows the normal kind of a metal, but at some temperature, abruptly the resistance goes to zero. Okay, so this is what is distinguishes from superconductivity from normal metals. Of course, the ideal metal it's supposed to go like this, but that doesn't exist. The ideal metal doesn't exist because there is always some defects, grain boundaries, defects, dislocation, and so on that will have a finite resistance here. And so, for instance, if you want to check how, let's take a resistivity of copper, which is 2 microohm centimeter at room temperature. It will decrease to about 20 picoohms at 4.2 K, and it will remain constant because of the disorder in the system. So there is no superconductivity in copper, whereas the mercury you have seen that it does go to a superconducting state at 4 Kelvin. What are the consequences of a resistance state? Immediately, you see that the flux threading the resistance still cannot change as long as the circuit remains resistance. How do you see this? Let's take a small ring, and this material we say that it is right now it's at the normal state where T is greater than Tc. The flux threading the circuit is cross-sectional area into the applied field, and this will induce a voltage which is minus A dBA by dt. And now if you say that you bring such two coils and then say that it goes below Tc, you will see that the flux inside is constant. It just cannot put this equation. V is minus A d by dt, and that is current I into R resistance L di by dt. Very simple equation. And when R is equal to 0, then these two becomes equal. Then you will see that L into I, the current, in A is the cross-sectional area, B is the applied field. So this is always constant. So the total flux threading the ring, this ring below the Tc, is always constant if it is a resistorless state. Now what happens? How do you measure this resistance? You say it is zero resistance. Is it really zero? So one way to do it is to take a superconducting ring, put a magnetic field, induce a voltage like here. Initially, the field penetrates into the ring. Then when the Tc is less than this, the field here, the current will keep on flowing into the ring because there is no resistance. So one way to measure is the field which is inside as a function of time. See, It is I naught exponential minus R by T. So I naught is the initial current. It is the current which you will measure by measuring its magnetic field. And then you can get an upper limit. So I'm not, so the field can be measured to an accuracy of 10 ppm in a standard way. And you can get an upper bound on the resistivity. So upper bound of a possible decay, you can find how much maximum the current can decay and the field can decay in the ring. So I'm not going to go through this math. It's a simple math. And if you do this, you will see that the resistance should be less than 10 to the power of minus 25 ohm meter. So it's clearly the resistance is immeasurable. So for all practical purpose, we take superconducting state resistance as zero. So that is not the only point. R is equal to zero is only one of the properties of superconductor. So later on, Meissner and Oceanfield. So Oceanfield was his postdoc. So so Meissner Oceanfield happens when electric current loop spontaneously appear on the surface of the superconductor in a magnetic field. These currents adjust exactly to compensate the magnetic field applied inside the superconductor, so that the total magnetic field becomes equal to zero in the sample volume, but the surface current develop the magnetic field which will expel the applied magnetic field. So what happens really? So T equal to greater than Tc, the field penetrates inside the superconducting sphere. But when T is less than Tc, okay, you see that the field is expelled from the magnetic field. So initially the field is penetrating and this field is expelled from the magnetic field. So these are the two gentlemen who discovered this. For some reason, it should be called Meissner-Rosenfeld effect. It was called like that, but in the recent books, you will find only a Meissner effect. But it is Meissner-Rosenfeld effect. Okay. So how does one compare this now, a superconductor with a normal conductor? Let's take an ideal superconductor. So what happens in ideal superconductor? You can use Maxwell's equation, one of the Maxwell's equation, del cross E is dou P by dou T. And if you put the electric field zero in an ideal conductor where the resistance is zero, the electric field is also zero. So what you will get is a constant. D is a constant. The flux inside the thing is a constant. So it depends on how you cool the state, final state depends on how you cool the perfect conductor. That is, if you apply a magnetic field, their field gets expelled because the field here has to be constant. And when you don't apply a field, apply a field, then you have a field inside. Here there is no field inside, so it will remain as a field inside, zero. Here you apply a field and the field penetrates and the field will still be there, even if you take the magnetic field off. That is because B is constant. Whereas if you look at the superconductor, you see that, you know, this is the superconductor. When you cool its magnetic field, the field is always expelled. The final state is the same, irrespective of how you prepare the superconductor, whether you apply a field and cool, sorry, when you don't apply a field and cool, where you apply a field and cool, it's always the field is zero. So superconductor is much more than a perfect conductor. Okay. And this shows that the perfect conductor will not be in thermal equilibrium because it depends on the history in which you have applied the field and removed the field. Whereas here, it's always in thermal equilibrium because the field is expelled. Here, whether you apply a field before its transition or after its transition. So that is the reason why superconductor is amenable to thermodynamics. So, so, so when this happened, Cotter and Kashmir in the 30s, they developed a phenomenological theory. So, so the superconductor was thought as a, you know, a collection of normal electrons and the super electrons with the density of ns and nm. So when T goes to zero, you will have fully superconducting electrons, and go to Tc, then you don't have any superconducting electrons, it's just the normal electrons. So this is called a two fluid model. So London used this true fluid model to explain the electrodynamics of superconductors. Normal electrons has resistance, the superconducting electrons flow with no dissipation. So this is the superconducting velocity, and that is equal to the minus E. Then the current density is given by this expression, and that is the first London equation. That is J equal to Ns number density of the superconducting electrons E squared M into the electric field. So that is the first London equation. Then he combined this with the Maxwell's equation. As I told you, that the Maxwell's equation for a perfect conductor, B dot is zero. That is here, you can see that. So B dot is zero. So, but London said this whole expression inside this parenthesis has to be zero if you want to see the Meissner effect. Because Meissner effect says that not B is constant, but B is zero. because it behaves like a perfect dam. So there are several ways to derive this Meissner expression. I'm not going to do that. So based on the two fluid model and combining with Maxwell's equation, so he was able to write London was able to explain the how the field. This is the superconductor. This is in the free space. You apply a magnetic field, so the magnetic field goes down, decreases as you go towards the superconductor. And he was able to give an expression, okay, for a simple slab by using this his b as a function of distance, and this is the lambda L is the London's penetration depth. So people quickly measured, sorry, people quickly measured the penetration depth for various superconductors, indium, lead, aluminum, niobium, and so on. So, so the London was able to explain how the magnetic field penetrates into the superconductor. So then this was a really a breakthrough in understanding superconductivity. You know how to understand Meissner effect, how it expels the magnetic field. So the expulsion of magnetic flux in the supercurrent also decays, vanishes in the bulk, and magnetization is so the magnetization also changes as a function of Tc. So and this when you apply a magnetic field, you will see that the critical field which was at 0 degree Kelvin decreases as a function of temperature. So this was also done from the thermodynamic analysis, which we'll see. So the critical field, that is, you apply a field to a superconductor, its Tc decreases, and it decreases in this fashion. It's a parabola. Okay, and the magnetization will look like this. You have initially it's a perfect diamagnet. At the critical field Hc, it goes from a superconducting state to a normal state. So this is how one could understand the superconductivity. And so there was one great experimentalist called Pipard. So he was trying to do the experiment. London gave a theory, right? He gave this penetration depth as this fraction. This is the superfluid density, and these are all standard. C is the velocity of light, m is the electron mass, E is the charge, and so on. And so he decided to measure for a standard system like tin. Okay. Earlier, of course, it was measured later by Devlin, who measured the lambda as a function of temperature T by Tc. And you see there is a nice variation and it diverges close to Tc as it expects, because then there will be a full penetration when it goes to a normal state. But what Pippa did was, so this was the experiment which showed how the lambda behaves as a function of temperature. But what Pippa did was is to slightly add some traces of indium in tin. Then he found that the penetration depth decreases as we increase the indium content. That is, that is you the mean free path. You know, for a pure metal, it's around 800 nanometers pure tin, and then it increases as you put more and more indium into the system. Whereas the London's theory shows that it should not change. So, of course, it's an anomalous thing. Nowadays, we will simply say that, okay, the theorists have to work hard to understand how the impurity affects the penetration depth. But Pipard didn't do that. In those days, number of people working in the superconductive area are quite less. So Pipard decided to give an explanation by simple intuition. Okay. So so lambda not only depends on T but also on impurities. So the penetration depth and the normal electron free path are related. Because what happens when you put indium in tin, the mean free path of the tin will decrease as you put more and more indium into the system. So Pipard said, no, no, the London's penetration depth lambda is only one of the characteristic length. See, he introduced another length called another important length called coherence length. Why did he do that? He said the superconducting transitions are extremely large, extremely sharp. It is 10 microkelvin for for a material like tin. It's 3.2 K plus minus 10 microkelvin. It's that sharp. So it has to be a collective property of large number of electrons. Otherwise, statistical fluctuation from point to point would broaden this transition. You would not get such a sharp transition. And lambda depends on the impurity concentration, while TC and critical field doesn't change. So London theory cannot explain this. Moreover, we need a positive surface energy of the order of 10 to the power minus 4 centimeter to explain the existence of normal and superconducting phase in the intermediate states of superconductor. You could also get an intermediate state in superconductor, and for that you need a positive surface energy, which London theory couldn't give this. So he said the electromagnetic response is it's non-local, not like a local expression which London gave. So the underlying idea is that the quantum state of the electrons forming the superconductor cannot be arbitrarily localized. The typical length scale of superconductivity is expected to be kBTC, and the electrons within this kBTC in the Fermi level will contribute pro- appreciably to the superconductivity. And we can see that the kBTC is the energy and divided by the momentum is the Fermi velocity, and the delta P is kBTC by Vf. So from the Heisenberg uncertainty principle, we can see that delta x cannot be localized more than this. Delta x will be something like this. And from this, he introduced the coherence length, which is proportional to h cross v by kBt. The beauty of this is that this is only a thought process. It is completely intuition of Pipard. The greatest thing is that this matches closely with the BCS theory estimate of the coherence length. So what Pipard did was, from his experimental data, he found that simple one length scale, that is the London penetration depth, is not enough to explain the electromagnetic properties of superconductor. We need to introduce something known as a coherence length. It is called Pipard's coherence length. So once I introduces that, so this length bears no resemblance to the London's penetration depth, hence represents a different length scale affecting the behavior of a superconductor. It can be interpreted as a characteristic length which measures the spatial response of a superconductor to some perturbation. So it is the distance over which the superconducting state develops at normal superconductor boundaries. Length scale of this kind was introduced independently. We will see that the Ginsburg and Landau's theory also introduces these things, which is closely related to the Pipard. Now, Pipard has not heard about this 1950 theory by Ginsburg and Landau because there was a complete, there was no contact between the Western world with the Russian world at that time. So the length scale also is not identical. The Pipard's length scale is temperature independent, whereas Ginsburg Landau depends on the temperature. We'll see that. And the Pipard coherence length is related to the BCS co-length, which is remarkable. But through his intuition, could able to do wonders on this. So what he did was, you this is an anomalous skin effect which we have studied in good conductors. What happens is that when the mean free path you know, compares with the classical skin depth, J will be not equal to sigma ER. This because the electron traveling up to the distance r will be influenced by all fields it has traveled before its last collision. So J will have a non-local dependence on r. So this was what done by Sondheimer in 1952. He suggested that J will be it's given by this expression, which will go to Ohm's law when E becomes a constant. So he took this analogy and then wrote an expression. This is the London's expression. So what Pippa did was to write a generalized expression for that, same as the way the anomalous skin effect was done in the classic electromagnetic theory. So with that, I'm not going to go into the maths. Pardon me for that. It will take a long time to explain this. So what I'm going to do is go to the final result. The final result is that J is going to be sorry, J is going to be a integral function. J will be this expression. J is going to be an integral function of the vector potential and the distance xi naught, which is the coherence length, which is introduced by the Pipard. So what happens in cases is that in cases where A is, in cases where the London's penetration depth is much larger than the coherence length, it will reduce to the London's equation. J is proportional to the vector potential AR. So, so but in many superconductors, at least in type 1 cases in metals, the coherence length is larger than the lambda. So London's work uh, will not uh, agree with the experiments. So now the new coherence length for the pipette will be given by this expression. Lambda cube is lambda squared into xi naught. So you have two different superconductors. And also for impurities, he has a nice way of explaining this. This is the London's expression, sorry, Pipard's expression, where he will change this xi naught into 1 plus xi naught plus 1 by alpha. Alpha is the mean free path. So as you know, when you add impurities, the mean free path will decrease. And so is the JR, which is given by this expression. So he was able to explain the penetration depth, which we saw as a function of impurities using this expression. So that's how we realized that he was right. So we have two kinds of superconductors. One, it's called the Pipard's superconductor, where the coherence length is greater than lambda, and there is a London's superconductor where the penetration depth is larger than the coherence length. So there are two kinds of length scale in this problem, and the magnetization varies depending on which superconductor you are. So the Pipard superconductor is called type 1. London superconductor is generally called type 2. We will see how it is. Okay, so let me just give you a recap of what we have discussed. We discussed the discovery of superconductivity of mercury and other elements. Then we said the upper bound for resistivity is 2.5 into 10 to the minus 25 microohmmeter. That is basically because even this limit is skimming because we can't measure more than 10 ppm accuracy of the field. So if you measure the field delta P better than that, this value will still go down. So all practical purpose, we take superconductivity as a resistance zero. Then we discussed the Maestro-Rosenfield effect, which showed that it is a perfect diamagnet. It is more than a simple uh, fictitious material where the resistance is simply zero. So it's more than that. So you have London's equations. This is the first London's equation, and this is the second London's equation, which goes to the penetration field. Then you have Pippard's coherence length, London's penetration depth, which is given by this expression, where lambda is greater than xi, and Pippard's penetration depth, where lambda is less than xi naught. Okay, so can we take a 5 minutes break and then come to the Ginsburg-Landau equations? Manoj, or should I tell a little bit on this and then go for the break? Manoj, hello.
Yes, sir. Yes, sir.
So what do we do? Should we just go to the take a break and come to the Landau's theory of phase transition,
Yes, sir. We can do so. No problem.
or should I continue for some more? It depends on what you feel.
You can split, sir, content wise. Actually, these four
Okay.
lectures are up to you, so you can
Okay.
divide as you like.
So I think let's take a 5 minutes break and we'll come to this. So next lecture I'm going to talk exclusively on Landau's phase transition, and the tomorrow's lecture is on BCS theory and Josephson junctions. So I think we'll take a 5 minutes break and then let us join at the 4 o'clock. 10 minutes break so that we will start on the London's theory of phase transition.
Okay,
Okay.
sir. Perfect,
Yeah.
sir. Yeah.
Yeah. One more
Thank you.
thing. One more
Yes,
thing,
sir.
I'm going to leave the slides with Dr. Manoj Kumar, and my email is there. You can have the slides and then work on it yourself. And if you can't, you can always reach me, and I will answer by email. Okay,
Okay.
fine. Thank you.
Okay, sir.
So
Thanks.
let's just take a break now. Hmm?
Yes, sir. Sure.
Okay. I'm waiting for Dr. Manoj Kumar to join us. Then we will start. Okay.
Yes, sir. I'm here.
Oh, sorry. Okay.
Yeah.
So let me start on Landau's theory of phase transition. So we saw the London's theory, and then we also saw about how Pipard introduced the coherence length. So things were not really clear at that point. How some superconductors have coherence length greater than lambda, and some are where lambda is sometimes greater than xi, and so on. So it became clear only when Ginsburg and Landau gave this phase transition theory. So this theory is general. It need not be only applicable to superconductivity. They developed it for a second order phase transition. You know, uh, superconductor is a second order phase transition in zero magnetic field. So is ferromagnetism. Paramagnetism to ferromagnetism is also a second order phase transformation. So what they said was, high temperature, there is a high symmetry phase, and the symmetry is broken at the low temperature phase. And this is described by an order parameter. So the order parameter is zero in the high temperature, and it is a finite value at low temperature. So close to Tc, the value of the order parameter is small. So it can be written, the free energy can be written in powers of order parameter, which terms allowed by the symmetry of the system. So you must remember that Ginsburg-Landau theory is close to the TC. Far away from TC, you have to tweak the theory a little bit. People have done that. So, but today I'm going to talk about the Ginsburg-Landau, which works closer to the transition. So the equilibrium value of the order parameter is obtained by minimizing free energy with respect to the order parameter. The order parameter for magnetization for a ferromagnetic transition is just magnetization. So the relevant symmetry here is the time reversal. Okay. So one can write the magnetization free energy of the system in terms of this A mz squared by 2 for 2 mz to the power of 4 and so on. The normal state, there is no spontaneous magnetization. And then at a below the Tc, it will develop a spontaneous magnetization with coefficients A is given by this, B is greater than 0, and the spontaneous magnetization develops when it goes from a paramagnetism to ferromagnetism. How does the free energy changes? Free energy, which was a parabola, will split into two local minima states like this at mz naught. So this is what the theory for phase transition in paramagnetism to ferromagnetism. So for superconductor, so the Landau, Ginsburg and Landau, this gave a similar theory. That is, this is Ginsburg and Landau. They said that the order parameter is a complex order parameter, which is Zr, which is the basic. And so later on, of course, we know that the building blocks of a superconductor is bound pairs of electrons. Okay. So that time, of course, they didn't know. They assumed that it's a wave function describing the center of mass motion of the Cooper pairs. All pairs are in the same quantum state. They call it condensed state. Also, the single value wave function of the superconducting electrons is defined by this. This is the number density of the superconductor into exponential E phi, the phase, and psi squared gives the mod psi squared gives the density of the electrons, that is ns. So the symmetry requires, they say that the symmetry U1 is broken. We'll see that when we go to the next slide. So initially they considered psi as a constant. So the free energy density depends on the density of the superconducting electrons. So what they said was free energy of the superconducting state is the free energy of the normal state plus alpha psi squared plus beta 2 psi to the power of 4. You can see that the odd powers of psi are not here. That's because of the symmetry. Because when I change psi to minus psi, this should not change. And for a continuous phase transition. So that's why the odd powers are eliminated from this. So what they did was the free energy, which was where alpha is greater than zero, it will be like this in the normal state. When the alpha becomes less than zero, you will see that the minima split into two minimas. And and the free energy so the minimize the free energy with respect to xi, you will see that xi is equal to xi naught squared minus alpha by beta. Alpha is negative because it is T minus Tc. So we are looking at temperatures less than Tc, so alpha will be negative. And so these are the expression which he gave, which they could find for this alpha and alpha and beta. And you see that when alpha is less than zero, this will have a two minima in the free energy. And so what they were able to show that all solutions with this value of psi minimize the free energy. In a given experiment, only one of them is realized. So the equilibrium state is an order parameter. Phi is equal to mod psi is e power I phi with some fixed phase. So what is happening in the superconducting? Which symmetry is lost? This is earlier the phi can into the e power phi can assume all values. Whereas in the superconducting state, there's going to be only one fixed phi. So that is the symmetry which is not invariant and the rotation of the space. So we say that the global human symmetry of the system is spontaneously broken since the free energy has it, but the particular equilibrium state, the superconducting state doesn't have. It has only a fixed value of phi, unlike all values of phi which has taken in the normal state. So this is called the U1 symmetry broken because U1 symmetry requires phi to take all values. So this symmetry is broken in the superconducting state. So that is how the order parameter is described. And note the expansion is fourth order is justified because psi is small. That is the reason why we are working at close to TC. The value of psi is small. And so one can also estimate the critical field by the free energy of the superconductor minus free energy of the normal state is minus alpha squared by 2 beta. That's what we saw in the earlier expression, which is nothing but hc squared by 8 pi. So this will give you an expression for HCT, which is the critical field, which is HC naught in 1 minus t squared. This is what we saw earlier. Most of the elemental superconductors, the critical field at which the superconductor goes from a normal superconductor to normal state is defined by this parabolic expression. You can see that, lead, tantalum, mercury, tin, indium, thallium, all of them show close to T minus Tc squared. So that is the critical field. And these are all type 1, which we call it Pippard superconductor because the coherence length here is much larger than the London's penetration depth. And we can also calculate the heat capacity. The heat capacity, the free energy is given by this expression. So the entropy is, sorry, so phi naught squared is minus alpha by beta, and psi square goes to zero. Order parameter goes to zero at the TC, and so the difference in the free energy is minus alpha squared by 2 beta. So the entropy is defined as the first derivative of free energy with respect to temperature. So when T greater than Tc, it is zero. So we find that there's no entropy associated. But for T less than Tc, you can see that there is a finite entropy value, and that is given by this expression. T minus final expression is this. So S is continuous at Tc implies the phase transition is continuous, not first order, it is second order. The heat capacity of the superconductor, which equals 0 for T greater than Cc, but it has a finite value for T less than. So one can show that the heat capacity has a jump of this value at Tc. And superconductivity and to normal state can be considered as a thermodynamic transition with variable parameters T and B. Stable state is the one which has the lowest free energy. So we want to compare the difference between the magnetic contribution to the free energy of two phases, superconducting and normal field. So you can see that the Gibbs free energy in terms of the Helmholtz free energy is given by beta H, and you can get the free energy, Gibbs free energy for the normal state, Gibbs energy of the superconducting state. You can see that the Gibbs free energy below the critical field, it goes down. And so this becomes the superconducting state is the stable phase. But as you increase the critical field, you can see that the Gibbs free energy of the superconducting state increases and becomes equal at the critical field. So it goes from a superconducting state to a normal state. Excuse me. So you can also compute the discontinuity in the heat capacity, sorry, jump in the heat capacity, which is given by the critical field divided by the transition temperature. So the phase transition is second order. Since the second derivative of the thermodynamic potential with respect to D is the lowest at the discontinuous one. So you can see that the entropy change is given by this expression where you see the associated latent heat, which is given by this. When you apply a magnetic field, it becomes a first order transition. Remember that superconducting state is a second order transition in with the presence with no field present, absence of the magnetic field. But it becomes a first order when you apply a magnetic field. Okay, so this is how the heat capacity was explained by the Ginsburg-Landau theory. You can see that this is the data for this is the data for the tin experiment, and you can see that the critical field, the heat capacity increase goes like this, and then shows the superconducting transition at close to 3.7 Kelvin. Then it becomes a normal state here. And when you apply a field of 500 Gauss, the superconductivity is quenched, and you can see that the superconducting, that is normal state heat capacity goes like this in the blue line. And you can clearly see this jump at the critical field, suggesting it's the second order phase transition, and that jump is proportional to the critical field squared divided by pi Tc. So I am not going through all the derivation of the thermodynamic relations and so on. This is called the Rutgers formula, and this varies within 1% of tin, indium, and so on. So it's extremely accurate to explain the heat capacity jump of pure type 1 superconductors. So this is the first consequence of the Ginsburg-Landau theory, who was able to explain the heat capacity jump, assuming that psi is constant. So, and suppose psi varies. Suppose psi is no longer constant with respect to r, but it is varying with phi naught exponential ir. So then the free energy will be changing. So it has a normal state, then they will have the same alpha of t plus beta t square, and then there is a variation of the gradient. This is coming because the psi r is not a constant of r, it varies with r. So, so psi r varies as a wave function of a particle of charge m, charge e and mass m star in the presence of a magnetic field. And in quantum mechanics, we know that the momentum operator is given by P, which is IH cross delta minus E star A by C is the vector potential. So now the free energy will become like this. You have a magnetic field which is coming in the system, and then you need to solve this. There is a kinetic energy and the magnetic energy, and then you need to solve this expression with respect to variation, minimized with respect to psi and vector potential A. So spatially non-uniform situation, GL added a gradient term, which what I told you is it's a macroscopic. This becomes clear when we go to the BCS theory, because those days when the Ginsburg-Landau theory came, it was very difficult to understand the macroscopic condensate and so on. But the proof came between the connection between Ginsburg-Landau and BCS theory. The real theory after the BCS theory was done, and it was Gorkov who showed the equivalence principle between the BCS theory and the Ginsburg-Landau. And why did we stuck with Ginsburg-Landau theory? Because this theory is very useful in application. Measure the critical field of a thin film, thick film, all kinds of things. It's much more easier to use than a BCS theory to calculate properties of superconductors. That's why it's still famous. Okay. So you can do all this math. I'm not going to do that. And so what we are going to do is to minimize this free energy with respect to xi and A. Okay, so if you minimize with respect to xi, you will get one Ginsburg-Landau equation. When you minimize with respect to the vector potential, you will get another Ginsburg-Landau equation. So I'm going to skip this algebra and go to the final Ginsburg-Landau equations. So you will get an expression. This is the with minimization with respect to xi, you will get this alpha phi by beta xi squared xi plus this vector potential term. This is called the first GL equation. Similarly, if you do a variation with respect to A, you will get another Ginsburg-Landau equation, which is called the second Ginsburg-Landau equation. I'm going to skip this math and then come to the final equation. So this is the second GL equation. Js is the superconducting density, current density, which is equal to this expression. And the current, this current, which has the same form of quantum mechanical expression for particle M star and E star, which you have read from your quantum mechanics. If you have a expression for the quantum mechanical current, it's quite similar to this, save for the nonlinear term which is there in this. It is the same of a Schrodinger equation for such particle with the eigenvalue alpha. Okay, so the nonlinear term acts as a repulsive potential for xi r on itself, tending to favor wave function which are spread out uniformly as possible in this phase space. So what we have done is that we have written a phase transition theory for a normal to a superconducting state in terms of the free energy. And then we minimize the free energy with respect to the order parameter and the vector potential A. We got two equations, Ginsburg-Landau equation 1 and 2. So let's see what we are going to do with this Ginsburg-Landau equations. First thing is that the flux inside a ring of a superconducting ring, earlier I said it is constant if it is a resistorless state. But if it is in a superconducting state, it is quantized. How do we do that? So you take a T, look at the TC, you take a ring like this, the field will penetrate, okay? And then the flux inside the system is B dot ds. D is the field. And so and it continuously varies in the normal state. As you increase the field, the flux will vary, in a continuous fashion. But when you cool this ring below Tc, the psi b changes discretely. It cannot vary smoothly. Why? Because from the Ginsburg-Landau second equation, we know that J is given by this expression, and J dot TL, if there is no current in the superconductor in this part of the ring, J dot TL is zero. Then delta phi into dl is given by this expression. So what happens here is that the total flux threading the system, the total flux threading the system will take only an integral multiple. The psi dot dl will can only take a value of 2 pi n, where n is an integer. So psi b is n phi naught, where phi naught is called the flux quantum. It is the constant. H is the Planck constant, C is the velocity, E star is the charge, which is actually 2E, because we are talking about Cooper pairs, which we will see. Okay. So this experiment was done by Douglas and Fairbank later in the 1961. They showed in hollow cylinders. These are really miniature cylinders, 8 millimeter length. The OD is 23 micron. The ID is 13 micron. Extremely small cylinders, because then only we can measure this jump. This is how you see. You vary the field up to something like 0.25 Gauss, it jumps to the next state, then it jumps to the other state. So it clearly showed that the phi inside this flux, it cannot take arbitrary value. It can only take phi b is n phi naught, where n is the integer. So it can take quantized steps. In fact, this was the triumph of BCS theory, because BCS theory said electrons are paired. So the charge has to be 2e. So this experiment showed that, the charge is really, the electrons are paired to give you superconductivity. So the point which I am trying to say is that in order to derive this expression, we fall back on Ginsburg-Landau. We didn't go to the BCS theory to explain. That's because we know by Korkov that there is an equivalence between the BCS theory and Ginsburg-Landau. It's easy to use Ginsburg-Landau to do all this compared to the BCS theory. Through BCS theory also we can show this flux quantization, but that involves second quantization and complicated quantum mechanics and so on. And can be done, but generally people use this to show flux quantization by simply using Ginsburg-Landau's. Then this covariance length. So let's go back to this. So I told you from London's experiment and Pippard's experiment. Pippard suggested a covariance length of psi naught, and London suggested a penetration depth of lambda. So there are two fundamental lengths in superconductivity. So Ginsburg-Landau's theory naturally explains how it comes about. So the first GL equation is given by this. Okay. And then we like to solve this. Consider the case when the vector potential is zero, when there is no current or magnetic field, then you will reduce to this expression. Okay. So the psi naught is minus alpha by d in the superconducting state. In the case of weak fields, we can say that, the A xi varies slowly with respect to x. So one can find, assume that f is equal to psi by psi naught and write an expression for a slowly varying function of xi r. And then you can compute this, and so what is, so this is something, what you get is xi square L T d squared f by df squared f minus f q is equal to 0. So psi L squared t has a length scale. It has a dimensions of length, and this is called the London's covariance length. Sorry, Ginsburg-Landau covariance length. And this is different from the Pippard covariance length, because Pippard's covariance length is temperature independent. whereas this is temperature dependent. Okay, it goes as T minus Tc. Uh, and it is greater than zero because we are talking about temperatures less than Tc. So Ginsburg-Landau has an equation as a natural way to get the coherence length. And how does this coherence length behave as a function of uh, the wave function as a function of xi? Then you can see that actually it goes as something like uh, tan hx if tan hx square root of xi lt, and the wave function goes like this. And so important thing here is that the coherence length, he was able to give an expression for it. Uh, that is, it goes as t minus tc to the half. And similarly, when you look at second GL equation, where we got this by varying the vector potential, and here you get this London's equation, this delta squared b by 1 by lambda squared b. So lambda lt and xi lt, Ginsburg-Landau penetration depth, Ginsburg-Landau coherence length varies as t minus t to the square root of so t minus tc. Sorry. So it varies as t minus tc to the whole power half, and then you can define a temperature independent constant called Ginsburg-Landau con- constant called kappa, which is the ratio of the lambda L by xi t. And so what you will see is there are two kinds of superconductors naturally coming out of the Ginsburg-Landau theory. One is a type 1 superconductor where xi is greater than lambda. You can see that xi is greater than lambda. Then there is another superconductor where xi is less than lambda. So what he suggested was, from his theory, he was able to calculate the positive interface energy for type 1 and a negative interface energy for the type 2. And how does this behave now? So for a type 1 superconductor, we have only a single critical field. It's a perfect diamagnet, low Tc and low critical field. So typical samples are lambda by psi is less than 1 by root 2, where you have tin, aluminum, mercury, and Tb are all type 1 superconductors. This 1 by root 2 is coming because the surface energy turns from positive to negative when kappa is less than 1 by root 2. This can be derived, I used to derive in my class, but that derivation is a little longer. And that was also used, derived from the Ginsburg-Landau theory, which showed that at the critical value of 1 by root 2, it changes from a type 1 to a type 2 state. So when in the type 2 superconductor, you have two critical fields, Hc1 and Hc2. Perfect diamagnet up to Hc1. The flux penetrates after the H is greater than Hc2. Then you have high Tc and high critical field. Typical elements are niobium, vanadium, and technetium. And most of the commercial alloys like niobium, titanium, where superconducting magnets are made, niobium 3 tin, they are all type 2 superconductors. How does the magnetization behave? So the magnetization for a type 1 superconductor, it's like this. You have a superconducting state, then it goes to the normal state at the critical field. See, type 2 case, there is a critical field, it behaves like a Meissner state only up to Hc1, then the flux penetrates. It's called the mixed state. And at Hc2, it goes to a normal state. So the critical fields, there's only one critical field here, type 1. There are two critical fields. One is Hc1, which is where you see a perfect Meissner effect, and then Hc2, where you have a mixed state. So the surface energy is, as I said, it is strong for strong type 1 superconductors. And Ginsburg-Landau showed that it persists for all kappa less than 1 by root 2. So type 1 superconductors tend to minimize the total area of domain walls. So one can do the surface energy for xi greater than lambda and psi less than lambda. So you can have a positive surface energy for type 1 superconductors and a negative. So as I said, kappa sits at the edge. When the kappa is one is the value. When kappa is less than 1 by root 2, it's a type 1. Kappa greater than 1 by root 2 is the type 2 superconductors. And this is some of the experimental values which you can determine. This is the magnetization of vanadium. You can see that as you go towards the higher and higher temperature, the critical field starts decreasing. And you can see that Hc2 as well as Hc1 in superconductor like niobium. Okay. So type 2, so we understand how the type 1 superconductors behave because it behaves like a Meissner-Gaussian, follow the Meissner-Gaussian field effect. The magnetic field gets expelled and it goes to the normal state. The type 2 superconductor is a different beast. It allows the field to enter after the Hc1. And so this was first seen by Shebnikov. So that's why it's called Shebnikov effect. He worked on lead bismuth alloy. Okay, for the lead bismuth alloy, we have a type 2 superconducting state. Domain walls have a region where the condenser is nearly fully developed, but the flux is not completely expelled. So the domain wall energy is negative. So it is favorable to form these domain walls in type 2 superconductors. So how does the field goes inside the mixed phase? Does it go randomly or does it go everywhere? How does that go? So system tend to maximize the total area of the domain walls. This tendency should be counterbalanced by some other effect. Otherwise, the system will become inhomogeneous on an atomic or microscopic scale. So then the GL theory cannot be explained, because it completely becomes inhomogeneous, then you can do that. And the flux quantization, the penetrating magnetic field cannot split into proportions smaller than the flux quantum. So we said that you know, there is a ring where we see a flux quantization, and this penetrating magnetic flux cannot be smaller than the flux quantum. So what people did was to show that the flux inside this, which they call it a fluxonium, which is given by this expression, fluxoid, which is given by the applied flux minus this supercurrent expulsion of the magnetic flux. This is again an integral value of the finite. And since the magnetic flux can only penetrate in the form of this modulo, this n phi naught, people showed, actually you can show by solving the Ginsburg-Landau equation, the magnetic field will penetrates in the mixed region in the form of fluxoids. This is a normal region. There is a superconducting current floating around. And these what they call vertices. And these vertices repel each other and they form a lattice. It's called the flux lattice because they form a at the normal at the center you have a normal core where there is xi is 0, and then you have fields completely penetrates this, and then the field gets expelled as you move away from there. So you can see that this is the xi 2 xi and this is the 2 lambda. So this is actually observed. This happens, as I told you, is below critical field HC, upper critical field, and above the HC1. And they seem to form a triangular lattice. Okay, it turns out that the free energy conservation, it has to form a triangular lattice, and the lattice constant is simply phi naught by root b. So when we change the field, increase the field, the separation, the lattice constant separation of this becomes smaller and smaller. At the critical field, it just vanishes. So the mixed state of type 2 superconductor is an unusual beast. We thought that, because it cannot have a inhomogeneous magnetic field distribution, the magnetic field penetrates in terms of vortices. And these vortices you can do by experiment. This is a bitter experiment where you can see, by spreading fine magnetic particles, and then the magnetic particles will go to this region normal, and you can form a trick lattice. Now, of course, we have optical techniques where you can neatly picturize this triangular lattice, and so that in sense is a hallmark of a precursor group of theory, which clearly showed this was done by Abrikoso because after the Ginsberg-Landau was successful in explaining many of the superconducting properties, Abrikoso calculated this mixed state, showed to Landau, but somehow Landau was not very impressed. But then the measurements came, and Abrikoso could publish his result, showed that magnetic field in the mixed state, that is between Hc1 and Hca, penetrates in the form of a lattice. Okay, so this it's a hallmark of a type 2 superconductor, that you have a lattice whose lattice constant can be varied by simply changing the magnetic field. We can also compute this. I am not going to do this computation. Depending on where xi is less than lambda, or the coherent length is less than lambda, or r is greater than lambda. So this is how the field penetrates. The superconducting fraction inside the vertex core goes to zero, whereas the field goes to maximum at this center. The current density also drops down. Superconducting current density also drops down in a single vortex. Okay. So, So the final expression for type 1 and type 2 superconductors, these are derived from the Ginsberg-Landau equation 1 and equation 2. So this is the critical field below which you have a Meissner state, where lambda is the phi naught, which is the flux quantum, lambda is the penetration depth, xi is the coherence length, Hc is the critical field, kappa is the lambda by xi Ginsberg-Landau coefficient, and ln k. So this is the critical field in type 1 superconductor, where you see an expulsion of magnetic flux. It will behave like a Meissner-Rosenfeld state. And then in the mixed phase, you will have this is greater than Hc1, and then the Hc thermodynamic field, it has no physical significance in this state in the type 2 superconductor. Then you have Hc2, which is the upper critical field, and this is the lower critical field. The upper critical field is related by phi naught into xi square t. It's the Ginsberg-Landau coherence length, and the Hc also you can compute the thermodynamic critical field as this. So Ginsberg-Landau was successful in explaining how the type 1 and type 2 superconductors comes about, and how the critical fields vary with respect to various parameters and temperatures. And in the mixed state, how does the magnetic field penetrates? It just doesn't penetrate in an homogeneous fashion. It penetrates in the form of vortex lattice and vortices, and these vortices form a vortex lattice. And that is the hallmark of Ginsberg-Landau. And you can see that, this forms a vertex lattice, and that can explain. the magnetic properties even on high TC superconductors like Hc2 for Pisco, it's about 200 Tesla, and YBCO it's about 170 Tesla, whereas the critical fields are extremely small, the lower critical fields. So they are called extreme type 2 superconductors because the kappa value, it's a ratio of Hc2 by Hc1. The kappa values are extremely large. So, so this is the typical experimental value of critical field in lead. You can see that at depending on the depending on the applied field, you can and different samples. That is, you start with the lead, then you add indium. See, the lead is a type 1 superconductor. So you will see only one curve like this, and this is the thermodynamic critical field, type 1. So when you add indium, slowly it becomes a type 2 superconductor. So for instance, if you look at the last curve where you have a maximum indium in this. So it's 20.4, it's a type 2 superconductor. So the critical field is close to 3600 Gauss, whereas the upper critical field, the lower critical field is extremely small, maybe about 100 Gauss or so. So this experiment clearly showed how the magnetic properties change as a function of indium concentration. So because the pure lead is going to a type 1 to a type 2 superconductivity, which could be easily explained by the Ginsburg law. Of course, if you have defects and disorder in the system, the magnetization is not going to behave as smoothly as this. The pinning will make it completely different. So this is the MgP2, another superconductor, which is really high, 39 degree Kelvin superconductivity. So this is the four quadrant magnetization. So initially it goes like this, then it becomes positive because the flux spinning. Then you reverse the field, it comes still positive. And then when you go back to this last quadrant, it becomes it has this kind of a behavior. So it's like a hysteresis loop. So this whole phenomena is happening because you have a disorder and then pinning. Whereas the earlier thing which I showed you, there is very little pinning in this system. So we can see that type 1 to a type 2 behavior very nicely, whereas these are extreme type 2 superconductors. So the magnetization will behave like depending on you have a type 1 or type 2 superconductors. The advantage of Ginsburg Landau, even after the BCS theory was published, people use this because it's easier to compute many of the parameters, superconducting parameters using that theory. So I'm just going to stop now here. And if there is any questions, I think I would request Dr. Manoj to collect it. And if there is any burning question, people can ask me now. Because tomorrow I'm going to deal with the BCS theory and then to the Josephson effect. Say, I have not touched upon any applications, and that would come tomorrow when you introduce the Josephson effect because it has a profound influence on the quantum computing. So it's important that you know what the Josephson effects are, and that would become clear after I introduce the Barden Cooper and Schrieffer's theory. Yeah, so I will just wait for your questions or
Yes,
comments.
sir. So, yes, sir, there are questions, and I
Okay,
will read one by one from the chat box.
okay,
So, sir, the first question we can take from Prahlad Rao BB.
yeah,
He's what is adiabatic? What is phonemic, non-phonemic?
okay. So you have to wait for my next class where I'm going to introduce BCS theory. Then I will tell you what is adiabatic and what is phononic and what is non-phononic. Okay, so this means you have to come for my next class tomorrow.
Okay, he also has some doubt regarding what is TC.
Tc is the transition temperature of the superconductor. So for instance, mercury, its Tc is 4.2 K. So below its Tc, it goes to a superconducting state where its resistance is zero, it's a perfect diamagnet, and so on. So Tc is defined as the transition temperature.
Okay, sir. There is another question from Ghosia Parveen.
Yeah.
How might superconductors impact renewable energy systems?
So I think again you might have to wait for the next class, but I can tell you. See, the superconducting, you must have seen the application of superconductor when you go to a specialized hospital, when you do MRI. The magnets which produce the large field of 1 Tesla, 2 Teslas, and so on, they are made from superconducting wires, which carry, which is cooled and which has no resistance. So there is no joule heating. So you can apply large magnetic field without dissipation, and you get uniform magnetic field. So that is the advantage of superconductivity in the medical field. Of course, we still have to use helium for this cooling the system, but people are now on trying to also work on high TC wires to produce fields at 77 Kelvin. The energy situation is that you can store this energy in superconducting magnets. Okay. So this energy can be stored and then it can be used as and when you require. Okay. So they are superconducting generators. So since the field doesn't change, once you induce the superconducting current, there's hardly any decay of the current. So these can be made to form superconducting generators where you can use the energy as and when you are required. In fact, there was a pilot scheme introduced more than 15 years or 17 years old in Long Island, USA, where they are using high TC wires for to light up the whole village. So the current carrying wires are superconducting wires, and the energy is stored in the superconducting generators. The whole village is powered by this liquid nitrogen cooled cable, and so there is absolutely no dissipation. See, the main problem of electrical connections which you see in outside, we lose more than 35% of current because of the dissipation, even high conducting copper. Imagine if you have a high TC somewhere around room temperature, then you do have a lossless transmission. Your energy what you produce is what you get at the site. So that is the reason why world over people are looking for higher and higher TC superconductors. Even liquid nitrogen, if you can find a stable long distance wire, it will save the energy. Maybe after 10 years, you will get back the money which you have put in.
Yeah. Okay, sir.
Yes.
I think this concern was clarified already from
Ah,
Devanshu. Usually we use suffix C to mark critical. So
correct.
should we term TC a critical temperature for the phase transition?
Correct. Tc is the critical temperature for the train transition. Because we call it critical temperature, is because that is the transition temperature. Okay. So,
Okay, sir.
and same as HC, which is the critical field, that is the maximum field which it can sustain. Beyond that, it goes into a normal state. Same as critical temperature. Below that temperature, sorry, just above the temperature, it goes to the normal state. So that's why it's called the critical temperature. Below which it is superconducting, above which it is normal.
Okay, sir. Yeah, so there is one more suggestion from Prahlad Rao that magnetic levitation in bullet trains is another application of
Correct,
superconductors.
correct, correct, correct. I will mention it in my next class. Okay, yes. You can levitate because it expels a magnetic field, right? So those trains are real. Actually, the Chinese have gone far ahead in that, and they can reach speeds up to 600 kilometers an hour and so on. And of course, we need to make sure that the wind resistance becomes less, so it has to go on and evacuated tunnels and so on. So it's just floating. The the rails are magnetic. The superconductivity is inside the cage, inside the carriage, and then it gets lifted. And they can travel because there is no resistance, no, there is no friction. So they can go as high as more than 600 kilometers an hour and so on.
Yes, sir. So another one, a little bit futuristic, maybe from
Yeah.
Lakshmi Narasimha Rao.
Yeah,
What is
think
the best
futuristic. That is very good.
superconducting? What is
Yeah.
the best superconducting based quantum computer across the globe based on your experience?
No, no, see, that I think you have to wait for the next class. See, there are several qubits. Right now, the qubits which are used for the superconducting technology is based on aluminum. And people are working on niobium. It's all pure metals only right now. So, because to make it uh, Jos array of Josephson junctions and so on, we need to have reliable technology which can be upscaled. And so far, there are only two contenders. Mostly it's aluminum. So there are some work going on with niobium qubits. So I think I will mention it in my next class when I talk about Josephson junction. So that is what is. So the quantum computing, there are competing platforms. One is this Josephson junction technology. You can have a qubit. Qubit means you have two states, 1, 0, and 1, just like your classical computing. So this kind of states can be achieved by photons. It can be achieved by cold atoms, neutral atoms, or even ion trap system. There are multiple platforms for quantum computing exist today. People must have heard that IBM has 1,000 qubits or something like that. Somebody has so many other qubits, 1,000 qubits for ion trap, neutral atoms using cold atoms, and so on. So there are competing platforms. It is still not clear which is going to be the winner for quantum computing. Everybody is doing, all these platforms are capable of doing quantum computing, but dust is not settled yet as to which technology is, each one has its own advantages and disadvantages. But the superconducting qubit is easily scalable. So, and that is how it is catching up. But the ion trap is also, it's going very far ahead in quantum computing. So it's just not settled. What is settled in some sense, which is going to come faster than all this technology, is quantum communication. So that is something which is going to come much faster than quantum computing. But it's an exciting phase. This is called the birth of second quantum and so on, because we are able to manipulate those qubits, all these extended states and so on. So the technology is there. So the engineers and the physicists have to work together. The physicists cannot do this alone unless they are backed up by the engineers. And there is a close collaboration which is happening all over the world, even in India, to achieve, you know, reliable quantum computing systems.
Yes, sir. I think this we can take the next question from AK Jha. Or what is the significance of computing critical depth, critical penetration depth? I think.
Yeah, so see, the penetration depth tells you about the properties of the superconductor, whether it is type 1 or type 2. Not only that, it also gives a measure of the superconducting electrons. You see, if you look at that expression of lambda L, it has the number density of superconducting state. So penetration depth is a crucial measurement to distinguish whether it's the type 1 or the type 2 superconductors. And also you must, when we use this system in a field, we must make sure that the penetration depth is small so that it doesn't affect the electronic properties of the superconductor. So we need to measure the penetration depth. It's an important parameter which we have to measure. And I didn't tell you the technique. We use a resonance technique to measure this penetration depth. You put this superconductor in an RC circuit, measure its frequency shift. From the frequency shift, you can get an estimate of the penetration depth. So these are, available in some books. Also in my slide, I will leave it with Manoj Kumar. You can have a look at it, how it's really measured.
Okay, sir. There are some more questions.
Yeah.
One from Anush Kumar. In
Hmm?
isotope effect, TC is inversely proportional to the square of m, where
Oh,
m is the isotope mass.
yeah. So he is going advanced. He is going. Tomorrow I'm going to tell you about isotope, right? That's correct.
Okay.
Say, because that tells you that the phonon mechanism is the one which, see, what is phonon? It's a quantized lattice vibrations, right? So this is the glue for making the electrons pair. So if the phonons are involved, naturally the isotope effect will come into picture because it will vary depending on the ionic mass, no? So that is what you are right. In some cases, it goes as 1 by square root of m r, but not all materials. Okay, that makes the system a little complicated. Luckily, during the BCS time, they only measured in uh, uh, tin, indium, and so on, where they showed a perfect 1 by square root of m r for the isotope effect. But there are things like uranium, it goes as n to the power of half. But that's because of some correlation effects and so on. But clearly, the isotope effect is a crucial experiment to show that the phononic mechanism is involved in TC. In fact, even in high pressure superconductivity, if you change the hydrogen by deuterium, you will see that the TC is decreasing, which showed that even on these high pressure superconductors, it is a phononic mechanism which is operating.
Okay,
We
sir.
will see that in the next lecture when we talk about BCS.
Yeah, actually, he mentioned a little bit more in the question that his curiosity was how the mass variation at nuclear level affect the TC, though superconductivity is associated with electron-electron interaction. So I
Correct.
think this will be addressed in the
Yes,
next
we
class.
will explain this in because the glue is phonons, right? So you will see the how the mass enters into the expression.
Okay,
See,
sir. I
yeah,
think possibly the last question and very interesting one is that superconductivity and superfluidity are interrelated things.
yeah. See, the superfluidity can happen. See, superconductivity can happen only in charged systems, right? You need electron charge, and superfluidity happens in in neutral atoms like helium-4. Okay, so it undergoes super. There is a connection, but that connection is which I will explain to you in my class when I discuss the superconducting theory. See, the superfluid state, it's basically bosons which undergo superfluid condensation like helium-4. So what happens as you go and lower temperatures? All this condensate, all of them becomes goes to the ground state. Okay, because they are all bosons. Whereas in superconductivity, only the electrons near the Fermi level are the ones which is contributing to the superconductivity. So those will go to the same momentum state. But what about the electrons which are filled up to EF? Those will certainly will have a Pauli exclusion principle operates there. So the superfluid state is much more easier to handle than the superconducting state because only the electrons which are close to the EF are the ones which are paired, which is a large number of electrons. Okay, but there are still electrons which is well below the KF. but they are all occupied according to the Pauli principle, right? It's not all electrons are going to the same momentum space or zero momentum space. It is in superfluidity that happens, can happen, but not in superconductivity. So only they are talking about only the electrons near the Fermi level. So that is the distinction between these two.
Okay, sir. So no more questions from participants so far. But
Okay.
I have a very small doubt
Please.
actually. Very often, a student ask myself when we teach superconductivity in the class that the history of superconductivity is like theory is behind the experiments.
Correct.
What could be the reason why we are lacking so much in on theory part?
Okay, so let me tell you about a little bit on the history part. See, the superconductivity was discovered in 1911. The first theory came after 46 years, 1957.
Yes, sir.
Okay, it's not that people are not working on it. People like Feynman and so on, who are one of the greatest theorists who worked on this and could not solve it. So, what happened is that there was a Bardeen was working on this for quite some time. Once he got the Nobel Prize for the transistors, he turned his attention to the superconductivity, and it it so happened that he needed a field theorist because to understand a little more on how to calculate the possibility of superconductivity and so on. I think Yang is the one who suggested Cooper. Cooper was a field theorist. So he was then, Bardeen gave him a lot of lectures on superconductivity, basic properties, and so on to get Cooper interested in this problem. And that is how Cooper, took these two electrons out just close to Fermi C and showed that it is unstable. The important part here is that theory is lagging behind the experiment because even BCS theory, they never bothered about the actual crystal structure or anything of that kind. They wanted to show that electrons can bind, form a Cooper pair, and that lead to TC. They neglected all the properties of normal metals and so on, anharmonicity, that, this, and so on. They were able to concentrate only on what brings the attractive interaction. They threw away the rest. And then the mistake they made is that it's a beautiful theory. It explains many of the things, predicted energy gap, and so on. But the important point is that they gave an expression for TC, which is a mistake. If they, at least they should have put a rider that don't take this TC expression too seriously, because that TC expression is completely oversimplified. They assume a Fermi surface and then spherical Fermi surface, they throw away less. Then the attraction interaction, they put a constant, it is within that, and then zero elsewhere. How do you expect the experiment, the theory to fit to all the complicated metals we use, So what people experimentally should have understood is that it's a beautiful theory, explained everything, but TC expression you should take with a pinch of salt. If the order of magnitude estimate comes from the TC, you should be satisfied because the basic mechanism is explained very nicely and they proved it. But actual things for each metal, there are so many things which is going into that. You look at simple metal like tin. It has a very complicated Fermi surface, right? Which we did experimentally found out. So to apply the theory, you need to do a lot more computation. And now, of course, because the last 10 years, the computation has raised to such a level that they can predict this. They can really show the TC of pin is 3.7K. They can do that. All this new computation technology, they can predict TC, not predict, they can clearly show that the TC is 3.7K from the fundamental theory. But this was lacking earlier, because so many material parameters which go into this, you can uh, never give a correct estimate just from the BCS theory. You have to go well beyond that. The important point is here is that no doubt BCS theory showed the electron phonon interaction is the responsible, but it failed to predict new TCs is basically because the theory is happened if you want to apply it to a real system. See, suppose this is a famous thing which I think I saw a lecture where Bert Mathias, he was extremely critical about the BCS theory. He said this theory never gave me a single superconductor. He has discovered more than 10, 15,000 superconductors, new superconductors. But then, when he was present, and some theoretician was talking about when you take A metal and a B metal and mix it, what is the TC? He was trying to explain. Then Matthias, after finished his lecture, Matthias said, suppose I take C element and D element, I mix, what do I get? So poor theoretician, he tried to calculate and showed some result. I said it will be like this. So Matthias coolly told him the experiment has been done, it goes in the other way. So the point is that that time, I think people were over ambitious to calculate TC and so on and so forth. Even now, if it is in pure metals, transition metal compounds and so on, the theory is able to clearly tell you what the TC is going to be. But there are cases like even magnesium. We were trying to look for superconductivity after Bismuth. Very hard. Actually, we tried to search down to something like 60 microkelvin. We went and we couldn't find the superconductivity in magnesium. And the theory, if you believe, it shows in milli K, and then they adjust the mu star and they pushed it down to 100 microkelvin. But still, we don't see the superconductivity yet. That is pure magnesium. Nothing is added there. And it is still open mark there. So, and in lithium, for instance, people predicted in milli K. Later on, it found it was at zero point 0.4 millikelvin. So what they did was to increase the screen Coulomb parameter mu star to a higher value. And of course, there are other experimental evidence why the Coulomb repulsion here, screen Coulomb repulsion is large in lithium. So that is why superconductivity is essentially material driven physics, because you don't know what to mix A and B and C. And earlier oxides are supposed to be bad for superconductivity. And that changed when Bernhard and Muller produced this lanthanum copper oxide, and later it went to a really extreme. But that brought new physics. You see, the point here is that you need new physics to explain higher TCs. Of course, the high pressure superconductivity was the only exception where it was predicted. Mermin predicted that if you take hydrogen, squeeze it in the form of metal in millions of bars, you would see a metallic state, and then ultimately it will go to a old high temperature superconductor because the theta D is about 3,000 Kelvin. So even with the phonon mechanism, it can be pushed to a higher temperature. Of course, people couldn't make a metallic hydrogen, so they took a hydrides and did that. So that is the theoretical prediction. That is the only prediction came from the theory as well as TC is concerned. But
Yes.
the real system at ambient pressure, we still cannot do this because it is the experimentalists who have to lead the way. That is how the scenario looks even now.
Yes, sir. It looks like that every material is a unique kind of thing, and it
Yeah,
requires unique consideration when we.
considerations
Yeah.
will do that.
So one more query from Devansu. Does any
Yeah.
volume of Landau's lecture of physics covered superconductivity?
Which one? No, I didn't get the
Landau's
question.
lecture of physics. I think there is a series of lectures or some books.
Yeah, yeah,
Landau.
there are books. Yes, yes. Landau series. I think you can look at, there is the statistical physics by Landau and Lifshitz, where
Yes.
they discuss this phase transition, Landau's phase transition, and so on. So whatever I have said, it is there in Landau's Lifshitz statistical physics volume. There is a series, no?
Yes, sir.
Okay, so that's you can look at that book. It's a classic.
Yes. So I think this is a general comment we see. Superconductor at room temperature created a big news in 2000, and many scientists taken back their claims. So it happened, I think, quite
No, no,
often
this keeps
sometimes.
happening. This is happening.
Uh,
It started with famous experiment by, I think I forgot that person. See, in 40s they froze ammonia, and then the ammonia, when it was cooled, it was showing some diamagnetic effect and so on. So people thought that they are seeing superconductivity at 200 Kelvin and so on. Then Mendelssohn just shook the cryostat and the superconductivity vanished. Okay, then there is this pressure quench copper chloride. This was the US work, and they applied a very large pressure and then suddenly released the pressure. It was showing diamagnetism, and then later found that it is just metal to insulator transition. And these results keep coming. I mean, that is the
yeah.
reason when Bednarz and Muller came in 86, there was a lot of skepticism also earlier, but that quickly changed when the Bell Labs produced also, other labs also started producing the ITC. So that was a genuine ITC system. So, so then there are a lot of see the point is that it's high stakes, it's a holy grail. You want to form a room temperature superconductor. So, and there are transient superconductors also people have reported, which could never be reproduced, you see. So my feeling is that there may be some budding experimentalist in the listeners. I think the problem is open for all of you. I don't think that nature is so convoluted that you won't have a ITC superconductor. It is just that our imagination, our thinking seems to have been limited. In my time, I really looked for a ITC and failed, I think. So, but then I'm sure that some of you would have success in finding them. It's a question of searching hard. People are using AI and ML and so on. They found some success in producing some low TC superconductors, but they were able to explain so far the high TC experiments found out by the experimentalists. They were not. There were some predictions, but so far I don't think anybody has shown experimentally such predictions are correct. It's still a problem. But
Yes,
people
sir.
keep looking at it because there are consortiums consisting of 4 or 5 nations who has invested more than $10 million on this to search for superconductivity. Various groups are looking for it. It's a it's a game where it's important that people could find some superconductor because it will certainly revolutionize what the applications point of view. Yeah.
Yes, sir. So it is already more than 100 years. And the interesting thing is, every 15, 20 years, we get something very exciting in this area.
Yes.
And then the excitement is ever
Yeah.
coming.
So
Mm.
see, that is the beauty of it because it's not just simply the high TC. When the oxide came, of course, high TC is a bonus, I would think. It is the physics which expands. People talked about non-Fermi liquids, marginal Fermi theory, all kinds of new concept in physics theoreticians able to bring, to the table, which was all possible because of the discovery of high TC. Otherwise, the edition wouldn't have bothered about it. New concept wouldn't have come. It enriched the understanding of physics. How much little we know and how far it can go and so on. So we need to discover new materials, new TC and so on, so that it brings new physics into the system.
Okay, sir. Thank you so much. I think
Thank you.
that's all from our side. And
Okay.
yeah, it was really nice lecture.